The ARDL model depending on your research question. So if all your variables are integrated of order 1, you can also specify an ARDL model. From the results of your bounds test, if the variables are cointegrated, you have to specify both the short-run model, which is the ARDL, and the long-run model, which in this case will be the vector error correction or the error correction model, as the case may be. But if the variables are not cointegrated, you can only specify the short-run model, which is the ARDL model. There won't be any need for you to estimate a vector error correction. Only specify the short-run model if the results of the bounds test indicates no cointegration. One of the advantages of using the ARDL model is that it is more efficient when you have a small sample size. In addition to applying the ARDL technique, you are going to obtain unbiased long-run estimates for your model. Now moving on to model specification. The ARDL PQ model is generalized in this way. We have YT, which is a dependent variable, being explained by its lag, and also the currents and the lag values of the regressors. I have denoted the lags with P and Q. The P is associated with the lags of the dependent variable. That is, the lag values of the dependent variable takes the alphabet P, while the lag values of the regressors take alphabet Q. So you often see the ARDL model being specified as ARDL PQ. So the P's are only used for the dependent variable, while the Q's represent the lags for the regressors. Also know that Y in this case could be a vector, just like I said, depending on your research, depending on what your study is all about. Y being a vector implies that all the variables that make up this model can also be used as a dependent variable. So that is the simplest explanation I'm going to give you for what a vector implies in this case. The XTs are the regressors, and they can be IO, they can be I1, and they can be cointegrated. The beta and the delta signs here represent the coefficients that we are estimating. Gamma is the intercept or the constant in the model. I can range from 1 to k. I in this case represents the number of variables in the model. Again, PQ are the optimal lag orders. Remember, P denotes the lag orders for the dependent variable, while the Q's are used for the lags representing the regressors. E is the vector of error terms. So all I've been saying is what I've also stated here. The dependent variable is a function of its lag values, the current and lag values of the exogenous variables in the model. Also know that the lag length PQ may not necessarily be the same, unlike a VAR model where you have equal lags for all the endogenous variables in the model. It's not the same under ARDL. The PQ may not take the same lag numbers. Again, the P lags are used for the dependent variable, while the Q lags are used for the regressors. For you to perform the bounds test, the conditional ARDL PQ1 Q2, because I'm using 3 variables now, so I have ARDL PQ1 Q2. Again, the P represents the lag orders for the dependent variable, while the Q1 and the Q2 represents the lags that the regressors will take. So for you to run your bounds test, you have to specify your model in this way. But before I show you the model specification, this is the hypothesis for the bounds test. The null hypothesis is saying that the coefficients of the long-run equation are all equal to 0. And by that, it implies there is no cointegration, against the alternative that these coefficients are not equal to 0. If we are unable to reject the null hypothesis, then we can only specify the short-run model, which in this case denotes no cointegration. But if we reject the null hypothesis in favor of the alternative, then we go ahead to specify an error correction model or a vector error correction model. I'm using 3 variables, and for simplicity, I have spelt them out here, and I have also color-coded them for you to know the way these variables are arranged in each of their respective equations. Remember, yt is a vector, and I told you that a vector in this case simply means that each variable in the model can be used as a dependent variable. So here I have LMVA, LNIMP, and real exchange rates. I'm looking at the relationship between the log of manufacturing value added, the log of imports, and the real exchange rates. So specifying the Barnes test cointegration implies that I am going to carry out 3 cointegration tests. The first one will be log of MVA as a dependent variable. The second test will be the log of imports as a dependent variable, while the third one will be the real exchange rate as a dependent variable. So I'll be carrying out 3 cointegration tests in this case. And these are the betas. Beta 1,1, beta 2,1, beta 3,1. That is what I'll be testing to know whether there is cointegration in the long run or not. If I'm unable to reject the null hypothesis, then I can only specify the short-run model. So you can always specify your model for bounce test in this way, depending on your variables and the structure of your model. But if there is no cointegration, you only specify the ARDL model, and you can see here you have the difference operator. Comparing it to the long-run model, you don't have a difference operator here. So note the differences again between the long-run specification and the short-run specification under ARDL. So you can also see here the difference operators are included in the equation for your ARDL when there is no cointegration. So I'm only limiting it to the first variable. You can do the same thing for all the variables in your model if there is no cointegration. This is the way they should be specified. But if there is cointegration, you can bring back the difference operator, because now you are going to specify both the short run and the long run. So in specifying the short run and the long run, the difference operator must be included when you are specifying your model. And here you must include the ECT, the error correction term. This one represents the long run representation or the long run relationship in the model. So the first part captures the short run from here to here. Anywhere you see the difference operator, these are the short run estimates. And here, where you have the ECT, represents the long run. And here I have explained the characteristics of this long run equation, that is the error correction model. Lambda, in this case, is a coefficient or the parameter of the adjustment term. That's the speed of adjustment. And it must come out with a negative sign after you have done your estimation. It shows that there is convergence in the long run. If it comes up with a positive sign, it means that your model is explosive. There is no convergence. So it must come out with a negative sign. And this is a mathematical representation of lambda in this way. Again, I'm going to explain the error correction term. This is the mathematical representation of the error correction term. Again, it captures the long run relationship in the model. Under the error correction term, you can see here theta xt. Theta is simply the long run parameter. Theta is simply the long run parameter in this case. While the A1i, A2i, and A3i, just like I explained earlier on, are the short run coefficients. So these are short run coefficients in the model. So look at the way the two are specified. This is when there is no cointegration. This is the short run model under number 12, and under number 13 is if there is cointegration and you are specifying an error correction model or a vector error correction model if there is cointegration across all the 3 equations being specified. I will conclude by saying that the outcome of the bounce test will tell you whether you are going to use a VECM, an ECM, or an ARDL model. Remember, if there is no cointegration, you don't need this part in the model. All these parts should not be included if there is no cointegration. But if there is cointegration, this is where you specify the error correction term. It will include the short run and the long run relationship being captured by the error correction term. So specify only the VECM only if there is cointegration from the 3 equations. Supposing I carried out the bounce test and there's only cointegration in one of the equations. So that means I'm going to run ARDL for 2 of them and only 1 ECM. So VECM is applicable if there's cointegration from all your equations being specified. You can also obtain short-run dynamic parameters when you estimate the VECM or ECM. I showed you that. These are the short-run parameters. The A1i, the A2i, and the A3i captures the short-run coefficients. And you can also know causal effects from the statistical significance of the t-statistic. So if the t-statistic of these coefficients are significant, then you can know the direction of causality from the regressor to the dependent variable. So if, for instance, if A1i is statistically significant, then I can say that the lagged value of manufacturing value added has a significant causal effect on the current level. And also, if, for instance, A3i, which is the coefficient of the real exchange rate, if it is statistically significant, then I can say that there is causality from real exchange rate to the log of manufacturing value added. Likewise, for the long run causal effect is captured by the significance of the lambda here, which is the parameter of for the error correction term. So if this parameter is significant, then it tells you there is long run causality among the variables. Finally, you interpret your short run coefficients using your ceteris paribus interpretation, because these are simply OLS estimates. So give them the same ceteris paribus arguments. Thank you for staying with me. In my next tutorial, I will talk about model estimation. Thank you for watching. Subscribe for more videos from Crunch Econometrics. Visit our website and our blog. Send us your likes and your comments.